Nice to see so many of you here early. Let's kick off this Unreal Fest then on the simulation track. Hello, my name is Visalteri Pimia. I am a 40-year-old software developer from Helsinki, Finland, and I work as the resident Unreal specialist software developer at Varjo, helping our professional customers in defense, automotive, research to make the most of Unreal Engine with Varjo's mixed reality headsets. The topic of this session is multi-app compositing, and the goal is to go over some of the history on how we got here, where we are today with mixed reality simulations, and how Unreal Engine, OpenXR, and various hardware and software stack enables complex combinations of software applications to work together, and how we can use that to produce simulated worlds on Varjo's XR headsets, using Unreal as a key technology with its advanced nanite geometry and lumen lighting to provide photorealistic scenes at high resolutions and frame rates. So before we dive into today's topic, short intros on Varjo and me. Varjo is a Finnish company dedicated to making the highest-end mixed reality headsets available for professional customers, with our current flagship device, the Varjo XR4, as seen in the image here, being on the forefront of XR technology. My background is in game development, and I've been professionally working exclusively on VR and XR projects in Unreal for the past 3 years. At Varjo, I provide consultation in the use of Unreal with Varjo's XR devices for our customers, doing training in the defense space, designers in the automotive sector, and researchers at various universities across the world. I also work on Unreal-based demos and examples using Varjo's technology, and also write the documentation for any of the Unreal stuff. So let's start with what is multi-app compositing. So let's start with a few words why companies and governments want to use multi-app in training personnel in mixed reality. Varjo's core customer segment in training and simulation in defense and aerospace. In this space, whilst not totally equivalent, game engine-like visual generation engines have been called image generators. Image generators are a combination of hardware and software that create real-time, immersive visual environments displayed to trainees, such as pilots, medics, and soldiers. IGs predominantly produce out-of-the-window scenes, sensor displays, and other visuals from a virtual database, using advanced rendering and often leveraging gaming technology to simulate complex, high-fidelity training scenarios and enhanced realism. Image generators traditionally may be a cluster of computers containing highly confidential map and terrain data, and as flight and combat simulators began to integrate computer-generated imagery created from real-world measurements, like satellite photography, this material would also be classified as something vital to national security, and thus requiring limited and controlled access to it. Internet access is tightly controlled in these environments, so the image generator may be securely separated from the XR headset, client computer, and simulation cockpit setup. Varjo supports this setup of secure hardware and software with the XR4 Secure Edition headset, as seen in the image, which includes offline installation and activation support, so it may be used in an environment without any internet access. Sometimes our customers are tied to using legacy applications as well, making it a requirement to combine older and newer technologies and applications, and sometimes even multiple incompatible rendering APIs. These are but a few reasons why multi-app is sometimes a necessity when rendering mixed reality content in training and simulation applications. So what is multi-app compositing? Instead of one application rendering the background, foreground, and UI, any of these elements may be distributed between multiple apps that are composited together in a final compositing pass, courtesy of our custom runtime. Each layer and app has a priority and layer flags that allow advanced control over the layers compositing, for example, a heads-up display that has fixed priority to always on top. A priority is a number. It may be positive, negative, or 0, and a priority is a Varjo native concept. In the next video, we'll see a first-person view from the simulator cockpit shown in this photo. And we will see there how we can turn on and off different applications in a 3-application multi-app example scenario. This is a photo from our office in Helsinki. So here we have 3 applications. We have a desert in the background as our terrain generator or image generator application, rendering using a native legacy application. On top of that, we render the spaceship cockpit with Unreal, utilizing Lumen and Nanite for photorealistic dynamic lighting and high detailed geometry. We have that wonderfully moody emissive lighting from the interiors from the displays without setting up any light sources in the scene, very important for assessing intricate details on a complex surface and form. And on top of that, we have the HUD layer running another legacy application as well. We also then utilize a predefined mask to cut in the simulator cockpit in mixed reality. All this is composited together in our custom compositing step. And you can see there how I was turning the applications on and off as well. So each app doesn't need to be aware of the others at all, but they can be if they need any intercommunication. Each app may even be technically incompatible with each other if they use the Varjo native API to set the priority. Each app receives the same head orientation from the headset, which allows the same viewpoint and head movement in every app. Any Varjo features may be utilized in any of the applications on the stack if supported. Like I said before, multi-app compositing is rendering API agnostic. You can mix Vulkan and DirectX without any issues, as each layer is composited from layer color and metadata. And this is also rendering and engine agnostic, so any of these apps can use any engine to render itself. So, OpenXR and Unreal. So Varjo's priorities default to priority 0 for Unreal or any application that doesn't explicitly set it. We can utilize this fact for the other apps in the multi-application stack to set their priorities to negative, so they appear behind Unreal's rendered image, or we can set them to positive, so they appear on top of Unreal's rendered image. We may also render more than one layer in Unreal and internally sort these as wanted. We have also internally implemented separate OpenXR layers with compositing flags that allow Varjo's compositor to handle them with special compositing logic. So here's a demonstration. Unreal defaults to priority 0 in the compositor. In this scenario, we have 1 to 3 apps running along Varjo's runtime, and we bring in the mixed reality video from the headset cameras. Insert the masked terrain from our terrain generator or IG app behind the cockpit windows. Overlay the gray arch from the Unreal scene virtually on top, and with our cockpit simulator app, and then render the HUD layer on top of everything in a third application, specifically locked to the user's face. This allows us to sandwich Unreal between 2 different applications with mixed reality video. We may submit custom OpenXR layers to our compositor that contain the rendering results from the new custom rendering passes, all in Unreal. How this is technically achieved is that we make an Unreal C++ plugin module and use fSceneView and the render dependency graph API to render to an external texture allocated on the OpenXR swap chain and add the resulting rendered layer to the current set of OpenXR layers using the OpenXR extension plugin interface in Unreal. We will look at some code examples on these later. Varjo also heavily relies on Epic's OpenXR eye tracking and OpenXR hand tracking plugins as well for our default implementation on eye tracking and hand tracking in Unreal. The rest of our custom features, like quad view for the custom displays and depth control, are also implemented as OpenXR plugins in the Varjo C++ plugin for Unreal. Our plugin extends Unreal and allows us to make custom releases for our customers with pre-release features before releasing the features to the public in the fab version of the plugin. Some custom example plugin features we've developed: headset view locked heads-up display, like I mentioned, a layer pass that's always locked to the view on top of everything. We've also implemented a custom mask mesh pass, as in we can cut in a cockpit around the user with dynamic control on the set of meshes from Unreal, so you can freely add and remove meshes from this set of masks while the game is running in Unreal. And this is rendered as a binary mask image in the plugin and as a custom fScene view as well. And we've also implemented a custom depth control layer So we can set depth occlusion near and far values dynamically while the application is running. So this is a simulator-style multi-app example consisting of 3 applications and 3 priorities. You have the desert in the background at -1 priority, Unreal Cockpit at priority 0, and another HUD application on top of priority 1, all 3 running at the same time on Windows. Here's a cockpit interior using Lumen and Nanite in Unreal 5.5. We have fully dynamic lighting here for the Unreal elements and full Nanite detail on the cockpit mesh. The background IG rendering the desert is using a legacy application to render a simple landscape. You can see all that nice green emissive lighting there. So shading and rendering technologies can be totally different in each app, but may result in visual inconsistencies. It's important to think about the final image and how it is to be composited together. Unreal may utilize Lumen and DirectX 12 for high-quality close-up details in lighting, shadows, and material shading quality. This is invaluable in fields like vehicle interior design, cockpit simulators utilizing time of day with weather simulation, and portraying hazardous situations in military simulations, where realistic lighting is important for analysis. Pairing this with Nanite geometry, this combination of technologies can be used to replace classic mesh level of detail workflow with light mapping and allow visually seamless high detail meshes at any distance with dynamic control over the lighting. We can utilize the power of Unreal plugins as well, and we do leverage technologies such as NVIDIA's DLSS to allow Lumen to scale up to the higher display resolutions needed by our mixed reality headsets, while still allowing fully dynamic lighting and deferred rendering techniques for getting that photorealistic mesh and material quality. We can also adjust the changes to the scene complexity and dynamically scale the image to stabilize the frame rate. Conversely, in a multi-app scenario, we can also render the background environment at a distance in much lower quality with a separate application, while reserving the highest detail for Unreal in the foreground. And it can have the bulk of the GPU and CPU resources allocated for that close-up detail. So next up, here's an example of a custom F-scene view rendering pass and how we can pass the results of rendering in an OpenXR swap chain to our compositor. We can set special flags for logging the layer on top and ignore headset movement to it. This essentially implements the HUD you saw before, and alongside the cockpit rendering in the same Unreal project without a separate app, without compositing performed, with custom compositing performed at the end. So here's an example in the OpenXR plugin. Essentially, we do have to create these swap chains for all the different rendering interfaces we have in Unreal. So we want to support all DirectX 11, DirectX 12, and Vulkan. So basically, you have the same boilerplate code to create the swap chains for those. This uses the RHI, or the rendering hardware interface, to achieve this. And here's how we then use that to actually create the swap chain images we're going to be rendering into. We register the plugin as an OpenXR extension modular feature, and we return any of the required OpenXR extensions for the pass in get required extensions. Both of those are our custom extensions. We then acquire the correct swap chain image and index on begin frame here, and then we inject this layer into the OpenXR compositing layers in update composition layers. Here's the header for the custom extended F-scene view, where we'll be accessing this swap chain image we just created and then rendering into it as a texture. So here first, we check that we are on the last view when rendering in either stereo or quad view. So in stereo, we'll have 2 views. In quad view, we have 4 views. We also make some accommodations for instant stereo here, and then check that the plugin has had time to initialize itself. Using the render dependency graph API, we render a face-locked quad into the swap chain the image texture. We get the widget texture from the player pawn, and we use that to get the contents for the heads-up display. This could be any UMG widget you want. And here's where we do the actual drawing using an RHI command list. We iterate through the view family views, 2 in stereo and 4 in quad view, and then draw the quad primitive into all of them. We get the custom path rendering into the swap chain, and then that gets passed to our compositor via the OpenXR composition layers for special handling. And the end result, as shown here, is that we have a custom HUD layer with special flags telling our runtime to log it into the view and ignore any head movements. And also to always composite on top of everything else, including the virtual geometry and the mixed reality video. So, some words about mixed reality features in training and simulation with our headset. So first, eye tracking. We'll look at eye tracking, including current eye focus area visualization, vision heat maps, attention, and reaction times. Next up, we have a video of the eye tracking heat map visualization. This is extremely useful for knowing, for example, which instrument your simulator pilots are concentrating their sight the most on, or which details in the scene your users are missing. So you get a very easy to kind of understand information from the eye tracking with this kind of heat mapping. This is a visualization what our eye tracking cameras see while you're wearing the headset. We can show a gaze dot in the mirror view for real-time display where the headset user is looking at the current moment. Eye tracking data can also be logged and exported as a CSV file for further analysis. This is not limited by the application frame rate either, so you'll get more detailed high-frequency tracking data from fast eye movements. Our current eye tracking rate is 200 Hz. So, multi-apps may not necessarily need to render anything, but they can just analyze or compute running completely headless. And real-time eye tracking analytics at 200 Hz are not limited what the frame rate is. And the tick rate can be much lower if wanted. Next up, hand tracking. We use this for controller-free interactions, hand joint visualization, and mesh control, and hand occlusion. Varjo newly supports automatic hand occlusion in the latest Varjo Base Pro versions. Here's an example video of the segmented hands rendered on top of everything regardless of the mask. This gives the lowest possible latency when displaying the user's real hands in the mixed reality scene. And as you can see, we can automatically cut it off from the wrist without any programming added necessary. Masking, we use custom mesh masks for exact compositing control, and we can create these mesh masks using our software called Varjo Lab tools. We'll also go through some how we use standard Aruco markers to track things in the virtual world, and a Blueprint API we use for detecting the transformation and showing and hiding of these markers. We'll also go through chroma key, how we can use the classic green or chroma key screen workflow for masking as well. So masking is used to create three-dimensional windows into the real world from the simulated world. And Varjo Lab tools, as shown here, can be used to create these interactively. We'll have a video of that later, what that looks like. And Varjo Base can then apply this mask natively without any extra rendering required from any of the multiple applications running in the multi-app stack. So here's the video of creating a mixed reality mask in Varjo Lab tools in the simulator cockpit setup. We mask in all the important displays and controls the simulator user needs to be able to see in the simulation software. And essentially, you just get a standard object file out of that you can then feed into our Varjo-based software. Or you can just use Blender or whatever to create these masks, whatever works for you. But I always found that interactively, you can exactly see where all the borders of your sim cockpit are going to be. So we use, here's an example of a Varjo marker. They're also called Aruco markers, pretty standard in the field. We use them to anchor or align virtual content with the real world. Each marker has a unique 3-digit number associated with it, so you can detect multiple markers at the same time and track them. Here's a moving marker used to create a 3-dimensional video plane, allowing 3 real objects to be viewed and tracked in a real 3-dimensional space in mixed reality. This example shows a moving map that is translated and rotated by the marker's orientation. Background world is once again rendered in Unreal. This could be used, for example, for viewing mission briefing notes, critical information, various tools, looking at your cell phone or pad, and of course, like in this example, printed maps. So our headset resolution is high enough that you can read your texts while you're in mixed reality. Our Unreal plugin provides the Blueprint API for detecting new markers and already detected markers moving and being lost. This allows tracking each marker's life cycle and movements. So very, very straightforward API. You have a unique ID for each marker. You get the position, rotation, and size, and you can pretty easily translate those into 3D transformations in Unreal. Here's a Blueprint code example how to react to newly detected and moving markers. So here I have a little bit of a custom logic to handle the plane moving in 3-dimensional space. And when I detect a new marker, I'm going to turn on the dynamic marker tracking mode for moving markers, and I'm just going to enable it on begin play. So the API is going to be detecting markers at all. And very simple integers to discern between these markers. So you can attach these to basically anything. They can be on the cockpit, they can be on a moving object. You usually want it to be something flat, that the marker should always be visible. So for chroma key, here's an example of me using our Helsinki office chroma key masking environment captured to the XR4. Some people who are familiar with Unreal demos can probably recognize this scene. It is the basement scene. And here's me just doing the classic Unreal, like green screen environment, have some props that I'm moving around, and this allows the classic chroma key workflow. And this is all rendered in Unreal in real time with Lumen and Nanite. As you can see, we have a pretty solid plane there on the floor, and I can move things around. Here's me tuning the chroma key values in Varjo base. This allows you to really optimize all the parameters for chroma keying in tandem with the mixed reality camera settings on the headset for best possible results. Because yeah, we're still going to be dealing with real lighting. We're going to be dealing with multiple cameras, so you really want all the camera settings and everything to be as great as possible. For example, in that video, I definitely wasn't tuning the values to be as good as they could be, but this really allows you to hone them in perfectly for whatever the environment is and save them. And the last pillar on this stuff is post-processing. The main thing we use is custom depth masking in Unreal post-process materials. We also have done, and I'm going to show an example of simulated night vision with green tinting and light amplification, and custom shader support in Varjo base for mixed reality video as well. So you can have a custom shader in the video as well. So here's the basic depth post-processing material for the cockpit simulator that we've seen. We composite opacity from custom depth and scene depth here. And then we get the final scene rendering result unaltered from post-process input 0. Very simple shader. Here's how the material is used to composite the mixed reality video image from the headset's cameras with the virtual scene we render in Unreal. Any application that is lower priority than Unreal's default value of 0 will be drawn on top of the video but behind Unreal. And yeah, what I really like about this that you can just have it running on the headsets on the table and tune these in. You don't have to even be wearing the headset. So here's a more complex post-material example. We'll use custom depth mesh locked to the VR Pawns camera for implementing a night vision circle scope that can be turned on and off by changing the post-process material. So here we have like a kind of an island scene, and this circular area is doing a little bit of light amplification and doing custom green tint on it. And here's the material to achieve that. So here's the implementation. It utilizes some pretty simple color math here. I literally got this from the Unreal forum, so thanks for that. Those forums are extremely useful for things like this. We combine the sampling from base color here and post-process input 0 here for light amplification on the night vision scope. And post-process input 2 very conveniently has the final scene without the custom depth scope mesh. So we can combine the results of the non-scope pass with the scope pass to produce the final image. So that was a very lucky coincidence. So the most dreaded topic, performance implications. So for multi-app performance, obviously these can all be optionally distributed. Each app and layer can be delivered by external textures, or it can be computed locally. We can use a custom-made server farm, for example, dedicated to just one of these layers of computation and rendering. Separate computers and server racks may be utilized for background app generation and caching for example, large-scale real-world environments. This allows the classic-style separation of an image generator and the overlaid cockpit simulator rendering setup. Unreal Engine with Lumen, Nanite, and DLSS from NVIDIA upscaling are well suited for getting the performance needed for a good mixed reality experience, but with selectively utilized dynamic photorealistic lighting. So here's me flying with the sim cockpit controls. Well, my colleague is actually. With very simple background generation, with more demanding cockpit with photorealistic lighting and high detail mesh on top. So you have the video from the sim pit, you have the cockpit from Unreal, you have the legacy app for the background. And here's the same session on the desktop, and here's me demonstrating how we can use Varjo's analytics window to monitor the performance while we're tuning the multi-application stack. We can freely shut down any of these applications while we're running and restart them without even removing the headset from your face. So here's me literally just starting an exe while Unreal's still happily running there on its own window. We have the HUD and we have the IG that's going to come up there soon on a separate window. And here we have 3 processing windows all in harmony, getting composited in real time. And we have those nice graphs telling us how much the application is it hitting the 90 or 75 FPS target, how much we're using the CPU and GPU there, what's the display latency on the headset, how much our compositor is using GPU and CPU resources. So this allows you to, as long as you're on green, you're probably good. So just kind of keep an eye on how complex each of these apps are. And yeah, you can shut down one app and see, okay, this had this much effect on the frame rate, and then start it back up and see kind of the overhead of each of these without having to do any more complex analysis on them. You can just, like you would start any apps on your desktop. So for optimization, you really want to make sure that each app is only rendering and processing what it absolutely needs for final display. You should optimize it for its purpose in the larger chain of applications, if possible. You have to be mindful that your GPU and CPU resources of the client computer that the headset is connected to will be divided between all these applications in the multi-app rendering. Plus, you're going to be getting various compositing and tracking on top of that. That's also going to be consuming some resources. Like everybody who's ever programmed from Windows knows that the current active Windows that's selected actually will play a role which process gets priority. It's really depending on how the application was developed and how it handles the events in Windows. So you should probably experiment which one is the most sensitive to being on top. You should adjust the rendering and CPU performance priorities of each app if possible. If you fully control the application stack, you could also try reserving CPU cores for each app, so that each app has a predictable set of resources available to it. Varjo Base has also some additional feature for synchronizing the headset to a fixed frame rate, and optionally we can also apply predictive motion smoothing to the rendered images. Not a silver bullet though. You can also tweak the pixels per degree or PPD resolution of the headset displays, and you can also cap the frame rate, refresh rate to 75 Hz instead of 90, which is the default high frame rate on the headset, to get some more leeway on the performance. You can also utilize multiple GPUs if possible, and split the workload between them. For example, one GPU can run the background app only, while the other one is reserved for overlay rendering only. Experimenting with the full application stack is necessary here for reaching best performance. Some apps may also even cap their frame rates or detail dynamically without it affecting any of the other apps. Complexity management is key virtue here when dealing with apps you didn't even necessarily develop yourself, or you might not even have source access. Remember that more apps with incompatible rendering APIs and techniques you have in the stack, more components you'll be analyzing. So know your stack well to utilize it to its full potential. We provide the analytics window with the graphs for showing detailed information on the current performance. So here's me analyzing the current performance in analytics window. This also allows me to analyze the current camera stream performance here. So how well our headset cameras are doing. We can see the application and compositor latency and the current frame rate with graphs. And we can directly apply VSync and motion smoothing here to directly experiment with the apps. You can also preview the stereo eye images here, so you can only show left, right, or both eye views at the same time. We can also utilize the Varjo Analytics window to visualize foveated rendering, using the yellow rectangle here to visualize where the eye-tracked high-resolution focus view is located. This is what we call quad view. Essentially, you have a less detailed area, which is the larger screen, and the yellow area, which is the high detail screen, where you're actually going to be looking with your eye-tracked view. And here we can also use the mouse for manually moving the more detailed area on the screen around in both eye views. This is extremely useful for debugging and analyzing materials and meshes that have multiple levels of detail based on distance and if the user is directly looking at them or not. So here's me. You can kind of see that blurry little rectangle there. That's the higher resolution area. We can also disable our real cockpit masking and directly interact with the virtual cockpit rendered in Unreal. As you remember that each application is running separately, so they can be executed as needed without affecting each other, making it possible to quit apps while the rest are running. We can use this to analyze performance. So here we have just Unreal and mixed reality. Remember, you should still optimize the Unreal-specific parts of the multi-app stack like you would any other Unreal project, utilizing the full suite of optimization features in Unreal. Use the stat commands in the Unreal console, utilize the various performance overlays and performance visualization modes, especially the shader complexity one is extremely helpful. Get the material complexity down as much as possible and make sure to utilize Nanite to its full potential here when dealing with high detail geometry. RenderDoc is also an extremely excellent external tool that we can use for understanding each frame and draw call, and it integrates really well with Unreal. RenderDoc can attach to any of the contributing processes running in the multi-app scenario. So, some future developments. We are planning some possible OpenXR extension support for multi-app layering. That would be nice to have in the future, combining these features in the standardized API. We will be exposing more Varjo OpenXR features via the Varjo Unreal plugin as needed by our customers as well. And more masking features are coming up soon, and these are very much also driven by our customer needs. Thank you for listening.